speaker this evening has over 20 years of industry experience. Please welcome the field CTO of MemSQL, Domenic Ravita.
Thank you. Thanks for coming out tonight. So it's the end of the NoSQL era. That is our bold claim, and I hope to convince you of that statement. I'm going to first take you a little bit to sort of how we got here as an industry. I'm not going to go way back in history, but I'll start sort of midway through that journey. Then I'd like to tell you a little bit of a customer story in action. Maybe you've heard of it, Fanatics. And then I want to show you something new for those of you perhaps who have seen MemSQL here before. Who's seen MemSQL here before at this conference? One? Yeah, a few people. Okay, great. So the story begins sort of in the internet consumer app Web 2.0 phase. Of course, before this, early in the 70s, we had sort of NoSQL kinds of data stores. Of course, they weren't termed that. But it were the challenges of the internet scale consumer applications. And I like to think of eBay sort of as the beginning point of this, from which Facebook, Google, and others, Amazon, sort of took some early techniques and further developed those in other ways. But at eBay, it's interesting because it was the beginning of just a very simple database, a single node database, Perl scripts and such, CGI at the time, and everything was in that one database. Nothing was split out, just a single node. All the searches, all the transactions through that. And of course, as that grew, the challenge was how to take the load off the database. Because searches were slowing down, you weren't able to get the kinds of transaction latency you required. And so eBay, and as others developed this later, provided a custom middleware or sharding approach to this, right? So that essentially you take a single node database and you start to partition either functionally or through some other means the data across these different nodes of the database. Each of those databases are just unaware, if you want to think of it that way, of what's happening in that application tier. And in the application server tier, this middleware layer helps for it to not have to, the applications to know where the data resides. It's basically a middleware routing strategy, and that layer that worked fairly well for several years, and that's middle period. To further take the load off the database so that they could scale for this massive kind of consumer driven volume, other strategies in terms of taking load out of the database, such as any kind of business logic, taking stored procedures, putting those in either in the application tier or in this custom sharding middleware layer. And then when it came to joins and sorts and things like that, those choices and those functions were then put in the custom middleware. So this middle layer, this tier here you see with the functional areas of, again, this is the eBay application, so catalogs, attributes, rules, account information, all of those were spread across these nodes like that. And this middleware layer became sort of now that's where the bottleneck became in terms of performance, and they could scale that horizontally. So after this period of where this approach now also started to break down, because the complexity of this middleware, shared custom sharding middleware, was such that it was not able to, they weren't able to extend it functionally well enough. So now the approach was just to basically take the database and blow it up, so to speak. Each function of the database split into its own application by function, and with a data structure that served it for the purpose. So we started to see things like, key value stores for front-end caches, and multiple types of caches. Search split into its own application, things like Lucene, later, which Elastic is based on, and others. And then we also started to see things like in-memory data grids. So a static object cache might be just a the assets of a web application, the JavaScript, things like that, the images. But the data object cache now is basically a different data store holding some ephemeral part of the data such that it can be provide faster read and writes simultaneously. And we see all kinds of examples of this. memcached was an early one that started to be used in this way. Coherence, TangoSolve Coherence was an earlier one that eventually became part of Oracle. And then later we started to see other varieties of these kind of special purpose NoSQL data stores. And they were NoSQL in that, of course, not only SQL, as you'd say, is that they broke the relational constraints of a traditional RDBMS. And all of it was done to meet the needs of the time, the constraints of the time, based on the hardware that was available and the software that used that hardware. So this was a better approach than sharding custom middleware across single node databases. And it came with a lot of pros, right? You get schema flexibility for the specific workload type. You get the language compatibility for if you're writing in Ruby on Rails or any of these other web applications. You had bindings for each of those. And they were distributed, and you get horizontal scalability across them. You get simultaneous scale for reads and writes. But again, there were some trade-offs here, right? Because now you're not having any sort of relational join. So when that has to be done, your logic has to be in the application to do this. In my own personal experience, working with some retailers and large transportation companies, we're doing things like at volume for a national retail chain where you're trying to have like global order track and trace and visibility for thousands of stores, and you're trying to track supply chain. These are classic use cases in retail, so that you don't, as a store manager, over order, right? So knowing the point in time at which orders are going to be delivered, where they are in the transit supply chain, which might be outsourced to a third-party trucking provider, for instance. So there's integration with typically EDI feeds and things like that that are bringing these orders together, all through different streams of data, different formats, and then you're trying to get basically the state of that delivery, if it's a retailer, like the state of the grill or the box of hammers or the box of dresses that are going to be delivered. And depending on what kind of retail chain you're in, this can vary vastly as to how important it is. If it doesn't sell in the next 6 weeks, it may be out of fashion. So it's very time critical to the business that real-time visibility and a track and trace basis from every perspective is available. But it's a massive amount of data. And typically the way, just continue with the retail example, this had been done previously, is they just couldn't provide that visibility to that granularity to store managers. They could say, run your query, you'll have data that's as recent as yesterday. So make your best guess judgment-wise. You've been the manager here for 20 years at this particular store. So it was less data-driven. There was, of course, data support. But, of course, it's much better if you can know more instantaneously to respond. Oh, this is the 4th of July weekend, and I'd like to respond to what I'm seeing now based on the campaign in this area and what I've got in stock, what's left in stock. And that's a much more dynamic question, but you've got to be able to source the data in these shorter time periods from these different sources. So the approach, and this is, circa 2010, 12, 13 time period, was you wouldn't be able to do that cost effectively by using a traditional single node database and scaling it up. So the approach that was used was to use like an in-memory data grid, track this information. It's great for the design up front in that you get really fast reads and writes to this sort of data fabric that's spread. But when you have to do queries that you had not planned in advance, that were not part of the application design process, you find that now you basically have to end up putting that data into some relational store after the fact. Or putting it into your next iteration of the application, in which case you are basically, because the code, the business logic is married to the data, you've got to bring the cluster down to that in-memory grid, do the change, bring it back up, load that data, and then the new view, which basically you can think of these as sort of logical materialized views that would be created in in-memory data grids like this, then you can start to get essentially that new query that's aggregated on the fly as the data comes in. So there are some other things you're giving up too, besides ad hoc queries, which is what I was explaining there. You've got data duplication. So you get this speed and scale and distributed scale out, but at the cost of lots of data duplication because it's not a normalized relational structure. So if I want to create these different views, I'm copying them, although they're in memory tuple spaces, I'm still having to copy them around to get the views I want. So your big fast data just got exploded even bigger, which means more machines. And these systems start to get into the hundreds of nodes. When you talk about doing this with something like Coherence or one of these other in-memory data grids. And when you're doing queries in the application, you get little to no query planning or strategies that a traditional relational database would give you. So you're doing the fetch from the space, you're figuring out in your application code how to join it. This has progressed a little bit since this time, but essentially it's not like the ease of development that you would have as an application developer against a traditional single node database. So as an industry, we've adopted all of these different types, and I've talked about one there with in-memory data grids, but we've sort of come to adopt sort of what the Valley has built for these consumer internet Web 2.0 companies in enterprises in many different industries. And sometimes it fits and sometimes it doesn't, but in the end what we're sort of, now that we're sort of 10, 15 years, you would say, into this era of the NoSQL era, what we start to see in enterprises is just a lot of different data store types. And for each of those data store types, you have to ask yourself, what do I have to do to support that? I need to have a different skill set to build for it, to design for it, to operate it. Whether that's on-premise or in the cloud, it's still another moving part. And you still have this application level complexity for things that you may want to do afterwards, ad hoc queries, or you have to decide to duplicate that data, bringing out of Elasticsearch, say, and then land it into some other relational store. So as 15 years of sort of the buildup of these additional data store types, it's starting to sort of crush under the weight of the management of this. And complexity in enterprise applications or the enterprise landscape is just, obviously you have to avoid that. First you provide the functionality, but then you're stuck with that infrastructure. And it's hard to unwind. So not only do we find that NoSQL data stores, even without that effect, because of organizational boundaries and change how data gets managed, you still have this effect of having to move data from an OLTP system to an OLAP system, or somebody needs a data mart for a particular self-service analytics. So you end up copying this and you're moving the data across each of these applications anyway. So this natural effect, which you're going to have a certain amount of this in an enterprise because you're doing this, the design of your enterprise information architecture is going to follow your organizational structure. Although some companies, some IT groups have decided how to sort of make a compromise and have a common services team that's funded separately and doing this. But in general, you're still having a lot of this, which you may not be able to get out of because this is what the organization drives. And that, of course, adds its own complexity there. So what does it mean at a human level for the folks who have to manage these data stores? Everybody, no matter what sort of job they have these days, is managing some sort of data, right? Tools like Spotfire and Tableau and others have sort of democratized the analytics on data. It's as easy as Excel, but much more powerful. So everyone has a different copy of this data. That's just sort of where traditional BI analysts are. Then you have a whole new, fairly new group of data professionals in terms of data scientists. They have a different workbench, a different tool chain. And what they're using often are R and Python libraries and things like that. They're accessing a data lake. Maybe it's Hadoop, maybe it's in the cloud with S3 or Azure Blobs or something like that. But essentially, they have their own tool stack. They're getting their own copies of data. And the role is sort of, it's not quite a DBA role. They're not managing often. They're not managing an operational transactional data system, but they have these side, analytic silos, so to speak. And the role is changing. And so there are a lot of stats here, but the U.S. Bureau of Labor Statistics had this over this 16-year period that growth in the DBA role has only grown by about 5%. That's a lot because the role is branched into other names, I would believe. Data engineer, DevOps. Some would say that automation is just eliminating the role, and I think it's just that the job is morphing and adapting, and you're no longer just going to be running a system, but also there are just too many systems that you have to run, whether you do those in Azure or AWS or GCP or running on-prem. Somebody has to be is responsible for each of these different data stores. So the role is blending in with a developer, data architect sort of role, and that's an increased scope of responsibility to have to not just manage fewer types of data stores as we traditionally were able to do before the IoT sensor boom and consumer and all this explosion of data, but you've got diverse types and the number of instances, and they're spread across the cloud and on-prem. So this complexity sort of hits home, I think, here at the human level. So our premise at MemSQL is that you've got to find an approach that unifies these different workload types and simplifies the infrastructure. And this is really the only way to get ahead of the complexity. And there's good history of databases that shows that this trend has happened where you see an early expansion of lots of types of data stores. We saw that in the 70s and 80s. And then a consolidation, and they start to converge again once the software architecture, the system architecture of these products catch up to what's possible in the hardware and in the IT environment. And we believe we're at that point today. So let me give you one concrete example. I mentioned Fanatics earlier. Fanatics is a sports merchandising company, and they basically provide online and brick and mortar sales channels for somewhere between 200-300 sports teams, professional sports teams across North America and colleges. So the selling of merchandise, they're like a one-stop shop for all of that. And it's very much a digital kind of business. It's about $2 billion in revenue a year. What they were finding was that they needed to modernize this infrastructure that they had. Basically, it's a customer experience-driven sort of driver for them, where everybody's expecting everything instantaneously. You order something, Grubhub, you order a coffee at Starbucks, it's just instant. That's sort of that mobile expectation is what every business, consumer, enterprise app has. And so they were missing out on some of this in terms of what was possible for them to provide visibility for their partners, like the Major League Baseball, but also the end user. And so they took on this basically modernization of their infrastructure. And it began with providing one common source of truth for the events that would originate in each of these other systems. And that's what you see here in the middle, called FanFlow, which is their event messaging bus. And so every new event that would happen across all these functional areas of payment, order, inventory, fulfillment, marketing tech, each of those events gets published over Kafka to the Kafka brokers here and consumed by other consuming downstream applications. So the first iteration of this to sort of bring the value and the timeliness of the data together was to ingest this data from Flink and S3 consumers over Spark and Redis. And so they used Redis for basically their in-memory cache. Elasticsearch was basically their persistent mechanism and the query engine. And they provide visibility into each of these data stores through these different approaches in the query level for different types of stakeholders, engineers, middle management, executives. Kibana was the way that they viewed this through for the executives, for instance. But they came to a point where this kind of isolated approach for each of the data streams became problematic. And they were looking for a way to simplify that. So they brought in MemSQL and basically were able to eliminate several tiers, several different instance types in that infrastructure, basically by replacing Redis, Elasticache, and Flink. And most interestingly is I think the ingestion part or the data integration part. With Flink, they weren't really able to integrate to many other enterprise data sources in the way that they needed to. And through MemSQL Pipelines, which I'll demonstrate for you shortly, they were able to do this data integration. So MemSQL is not just a database, although it is, of course, a distributed database, but it also provides this real-time streaming integration, which we call pipelines, that helps you to converge these different types of processing. So rather than do streaming aggregations in Storm or Flink or something external, when really what you're doing is you're calculating metrics and things that are kind of real-time analytics, you now can do this in the way that the industry was accustomed to doing it, which is sort of just in a relational database. You can push the compute back to the database. You can get your real-time metric aggregated, and you can get the speed and the concurrency that you want. And so that's what they took advantage of here in the case of their MemSQL deployment. So what is MemSQL? It is a multi-cloud relational operational database for handling multi-workloads for these new sort of applications. We can handle things that you would traditionally do in the example I just provided you with key value stores or search mechanism or an in-memory data grid or streaming applications. You can now rely on MemSQL to do that at massive volume. And so that's why we think of where we're at now as the end of the NoSQL era, and we're a few years into what we think of as the NewSQL era. You'll hear this term from different folks, different analysts, naming it something different: hybrid transactional analytic processing, or hybrid operational analytic processing, translytical. These are all different terms, but essentially they're fairly close with some subtle differences. And when I say that it's the end of the NoSQL era, I don't mean that you won't see more NoSQL data stores, because we still have mainframes. And people many years ago were saying, oh, client server, we're going to replace the mainframe. Well, the mainframe is really excellent at doing transactions if you treat it right. If you're an airline or a bank and you're doing transactions and you follow the working model of how the mainframe works, you can get massive speed and volume there. But there are other disadvantages to it. And so just as this transition into this distributed in-memory database era or NewSQL era, you're still going to find NoSQL. my point is just that you'll start to see a diminishing adoption of these. There'll still be more new variety and types, but we're not going to grow. It's not going to be this thing that's sort of like a wave. We think the next wave is already a few years in. So let me tell you more about what MemSQL is. As I said, it's a distributed database. It's fully ANSI SQL. So it's relational. And it provides an in-memory row store and a disk-based column store. And what that means is basically for, row stores are excellent for transactions. You're writing lots of data. When you're doing seeks and queries and updates, you're doing them on a few rows at a time in general. This is the data storage type that lends itself to transactions. Whereas disk-based column stores, and I would say row stores are typically you're operating on data in the size of millions to billions of rows, potentially. In the case of a disk-based column store, you're doing this for aggregations. You may be operating on data which is billions to trillions. It depends on sort of how much hardware you have. And I'll go into more details about the differences and attributes of each of those. As I mentioned in the use case with Fanatics, we also provide basically this integration framework called MemSQL Pipelines. And it allows you to ingest streaming data from S3, Azure Blobs, the file system, Spark, etc., Hadoop file system, and ingest that data, but not just ingest it in a single one-for-one fashion, but ingest it in parallel. And I'll describe a little bit more about how that works in just a moment. When you ingest the data, we provide a way to transform that data called MemSQL transforms. And this allows you to, in like a machine learning use case, you may be scoring the transactions against a pre-trained model as they're ingested and creating a calculated column from that on the insert. And these pipelines can call stored procedures, so you can chain them together, doing a transformation and then having another step through a MemSQL stored procedure. So very powerful ingestion here. I mentioned that this is sort of the NewSQL era, and part of what the NewSQL movement is about is that you handle these different types of workloads and maybe novel sorts of data types and structures. So we also have native JSON. So we can, if you're ingesting, say, with pipelines from JSON documents, you can take that data and insert the JSON whole object and query the object as a column later. You can also perhaps simultaneously flatten that or split it out and store that in a relational table. So the use case for that might be you're doing, you're a telco and you have some sort of billing application. You're getting JSON, XML documents, things like that. You know that your BI team has these particular queries, so you might do the work in advance, provide that in a convenient relational structure in MemSQL. They can query it with their BI tool of choice, but then after the fact, you expect them to sort of self-service their own. Maybe they need a new element from that XML structure or a new part of that JSON structure. You don't want to have to go back to the original integration team. They just query the column and pull the element out of the document from the column. So that's one kind of use case. Of course, if you're serving a web app, a mobile app, an API backend, you might want to just fetch the JSON so you can render that quickly in your iOS app, for instance, right? So you don't have to go to Mongo to have a whole different data store if this is your use case. You can have that document, basically treat it like a document cache, fetch the JSON object, and continue with the application. And this simplifies things for applications, because when one application has to basically be integrated with multiple data store types, it's complicated for the application development team. It's complicated when you're moving apps through the software development process and promotion process from dev, staging, test. All of it becomes more complicated. So if you can converge as many of these functions into a single operational data store like MemSQL, this eases your application development process. MemSQL also, and I mentioned this a few times, provides easy access from any BI tool. So any BI tool just looks at MemSQL as any other database. It appears as a single database. The fact that it's distributed is unknown to the BI client. And I'll explain a little bit how this connects later when I talk about the system architecture. And you can do any sort of ad hoc queries. Machine learning, I won't go into that today. That's a broader topic for another time. And of course, any sort of applications like real-time decisions, real-time applications. It depends on your use case as to what people consider real-time. But I would say, like in the Fanatics use case, real-time for them is about order tracking to the granularity needed for good customer service. Somebody says, where is my, where's my merchandise? Where's my hat? Where's my, signature basketball shoes? That sort of thing. You want to be able to have that quick, instantaneous response, that kind of order visibility. So often real-time means end-to-end from a mobile app might be a second or two, right? So that data has to be readily accessible, and really having something available through a fast column store in memory row store is about the only way to do that quickly. And finally, MemSQL runs anywhere. It's you can run it on bare metal, any Linux machine. We run in Docker. You can download this in Docker. I'm going to show you afterwards where to do that, cluster in a box. Or you can do this as a database as a service. And I'll show you that in just a moment. And actually, that's where I would like to get something started, which I'll come back to in just a second. So I'm going to come back to this in just a moment. I'm going to spin up a cluster of Helios here. Okay, and while that starts, that'll take a couple of minutes to start up. I'll continue here. So I mentioned database as a service, that is Helios. We also provide a Kubernetes operator, which is becoming sort of a more de facto way that you're deploying container-based applications here. So more about the row store and column store. Typically, the first question we get often about MemSQL is, MemSQL, it's an in-memory database. We get that from the name of the company. Is it only in memory? And so now you know it's not just in memory, but it's more precisely memory first. And it's memory first for the transactions in the row store, but also for the column store. So you can address a larger amount of memory than you have, a larger amount of data than you have in memory. That said, specifically for transactions, you've got to, for the row store, if you're using the row store, you've got to fit all of that data in memory. Of course, you're not confined to a single machine like you are in traditional single node databases, but the memory across the cluster of machines. So you add up the memory, all that. And all of the complexity of keeping the coherence and consistency of the data across that, the sharding of the data across all of those different nodes. MemSQL does all of that under the covers for you, and you have some control over that with how you create tables in terms of the shard key and things like that. So when you're using the row store, we're talking about millions or billions of rows of data. And you can stream this in real time and expect millisecond kinds of responses from it. You're updating specific rows, small amounts of inserts and updates and deletes on that. For analytics, you're storing that on, basically fast SSDs rather than spinning disks, and you're talking data in the size of terabytes to petabytes of data that can be addressed that way. As a column store, not only does the data structure of a column store help us to just pick out the particular columns for a query, but we also compress that, and we get really strong compression, sometimes as much as 80%. Of course, it depends a little bit on the data type and such, but a really high amount of compression to really use the disk space efficiently. So into the system architecture a little bit. So MemSQL, as I said, is a distributed database, and so every node in the system architecture is essentially the same, although it takes on a role. And the role is basically an aggregator or a leaf. Leaves hold the data, and the data is sharded across that, and that's what's depicted here through these green circles there, showing that like partitions of data across each of the leaves. For high availability, we provide a copy of the data. We don't provide 3, 4 copies. We just provide 1 copy for high availability. But we ensure durability through that and other means. Make sure that your data is written and it's configurable in terms of how the replication happens across the partitions and leaves so that you can get the maximum performance, but that you do get immediate consistency for what you need for the application. Again, this simplifies the application development. If you were to use something like Cassandra that's eventually consistent, you've got to write application logic with the knowledge that you might get dirty reads, right? You're not going to get dirty reads in this case. You can treat MemSQL as if it were a traditional single node database like an Oracle database running on big hardware. Yet it's distributed, but your application looks at it like a single node. So if leaves hold the data, what do aggregators do? Aggregators basically do the query processing. They receive the connection from clients like Tableau, Spotfire, any kind of BI client, that sort of thing, and determine how to process that query. You'll see you can make this redundant so that you have high availability of the aggregators by you'll have a master aggregator, but you'll have multiple child, and I'll show you that in the demonstration here in just a moment, what that looks like. And this allows you to get really linear scalability as you grow your cluster. The R in this diagram is basically showing you reference tables, lookup tables. So to my earlier example where, say you had a JSON structure that you might want to refer to, or it's a mobile app and you just want to fetch the document as the whole JSON object, that's a kind of reference kind of lookup, right? If you had company data, master data that might, reference data inside of a master data kind of approach, this is where you can have, and this can be replicated across all the leaves so that it's available there. So what gives MemSQL its performance and our claim that it's the world's fastest transactional and analytical database? One reason among several is that what we're doing with compiling queries. And I'll show you this in just a moment in the demonstration, that most databases, traditional databases, will basically compile this to an intermediate language and then execute that. You can sort of think of it like what Java does with a virtual machine or Python interpreter kind of thing. We're compiling this down to native code so that it's basically at the level of C, C++ language that's executing an executable. So that the first time this executes, it creates that, it generates that binary to call. Thereafter, you get the performance of not having to interpret this query again. So when you have, what the benefit of that is, if you have many, concurrent users doing that query, doing lookups, then you'll see huge improvements in performance there. And sort of interesting note about user behavior in terms of speed. And Google did a study a while back about search speed. And as they sped up the speed of their search, this was years ago, but I think it's been sort of repeated by other kinds of companies like that. When you increase the speed of that particular function, you get more hits on that function. You get more search queries because now you're sort of training the user that it is possible to ask and ask again and then ask again. And so it's sort of, once you make this improvement, you then get a sort of a volume of queries that you hadn't before for that. And that's what you want, right? You want to be able to do new things, open the doors for possibility. And this is what we look at with, for real-time operational analytics. So MemSQL Pipelines. I mentioned that as sort of an integration tool, right? The way this looks on the command line, I'll show you this in just a second, is it's just you're creating another database object called a pipeline, and it allows you to do exactly once semantics. So why is that important? That's important because when you're reading data from an integration stream, if you were to do this through ETL, typically what that ETL process is going to do, part of what you want it to do is to ensure that you don't have duplicates, ensure that you have all the data, ensure that you don't have some missing data. So exactly once semantics, when you're reading from something like Kafka, MemSQL pipelines deliver that so that you, in a sense, you're doing a kind of data cleansing, at least one small aspect of that. You could go further with the transformation to do more of that, to do lookups, matches, things like that on ingestion. And you don't have to do this in a third-party tool. So it may not solve all of your data integration challenges, but as much as you can to do this in one place and do it in a scalable way, this helps to simplify the ETL middleware infrastructure that you might have in your projects. These workloads or these pipelines come in parallel. And so that's huge speed. You can do this as a one-time basis, or you can choose to start from the beginning and continuously consume data as it appears at the source, the S3 bucket, the Azure blob, the Kafka broker, the stream, etc. So it's configurable in that way. And so if we look at how this works, is that when you define a connection in this way through a MemSQL pipeline to like a Kafka broker, the aggregator, the master aggregator for the MemSQL cluster will get metadata about that stream of data, basically the offsets for the Kafka partitions that it's pulling in. And then as many leaves as you have, they can make their own independent connections to each of these brokers and pull the data. And they'll each get some portion of the data, but this provides you you've eliminated any kind of input roadblock on the ingestion of the data. And MemSQL's special sauce is that it allows you to, or it provides this data shuffling to get the partitions or the portions of the data into their tables. Because as I said, right, if you had say an in-memory row store, the table is going to be sharded across these leaf nodes, and then MemSQL has to figure out where to take this data. If the data landed here in this partition, it may only be there temporarily, and that data may be written to this sharded portion of the table in this other leaf, etc. That all happens in the background. What you see as an application developer or as a data engineer is just huge ingestion. So if you can provide multiple sources from which to read, and it's matched roughly to the leaves, then you'll get really fast reads. And this can be your immediate real-time ingestion there. Let me advance this. There we go. So what's new with MemSQL? So I'm going to get the trivia question right. We've been around for roughly 8 years. This year we launched Helios, which is our database as a service. This is what I'm going to show you in a moment. MemSQL 7.0 is in the works. We're in beta at the moment. And we're adding some additional simplicity to how transactions and column-oriented tables are handled in something we call single store, to basically give you the best of those and make the design choices up front much easier for you. And there's some other lower level sort of improvements in terms of resiliency and sort of the UI of Studio, which I'll show you in just a second. And as a company, we're growing, we're hiring. Come talk to us afterwards. We just opened an office in London recently, so it's an exciting time for the company. So with that, I want to show you Helios. And Helios is not totally a new kind of technology. It uses MemSQL under the covers, but it's built for a cloud environment. And today we're running this in AWS and GCP. You get to choose your region. And it's on-demand, database as a service, all the things you would expect from that, which is that it's elastically scalable. We handle the patching, the upgrades, things like that. What you handle as the data professional or the application developer is your schema, your design of your tables. You make choices about the indexes and sharding. So there's a schema design responsibility on you, right? And that's something that any of these databases as a service would expect. So let me jump into this. Let's get my glasses here. And I started this cluster here a few minutes ago. So what you're seeing here is the customer portal for MemSQL. So whether you're using MemSQL on-premise with the binaries or you're doing Helios, this is sort of like your first one-stop shop for getting to our customer success forums, feedback, getting your licenses, things like that. So I just started this up in the AWS region, and now I'm going to launch MemSQL Studio. So what you see here is I've got a few nodes that have been started up. I don't have any data, I haven't defined schema, I haven't defined any pipelines, that sort of thing. I have some system level events on the creation that just occurred a few minutes ago, but no databases yet, other than the schema itself, the information schema. So what I'm going to do is use the TPCH data and use that to demonstrate pipelines and queries against those pipelines, but also the data that's being stored in the database. So TPCH is basically an industry benchmark. You'll find TPCC for transactions, DS for decision support systems. We've done benchmarks with all of these. My view on benchmarks is that really you have to look at your particular workload under your environment, your data access to sort of, but they do give you sort of a ballpark starting place, I'd say. So it's helpful, and this is available to you if you spin up your own Helios cluster. You'll be able to run this yourself. So I'll start with the first query here, and what I'm doing here is just creating the 8 basic tables for the TPCH. And so in the TPCH benchmark, you find customer, line item, it's like a retailer, country, nation, orders, part supply, etc. So basically a supply chain / order / front office customer CRM sort of slice of data. So across a few different business domains. So I'm going to run that here. to create the tables. And you'll see here in the panel below, I get status on those actions that I just ran there. Now loading with pipelines. And so there's going to be a different pipeline for each of these tables. And so let me expand this to show you. And then sort of show you the syntax of what a pipeline is. You know, as I mentioned before, it's like you're just creating another type of object in the database. And here, we provide lots of different sources, which I mentioned here. We're pulling this from AWS S3 buckets, and we're giving it sort of the specification to fit there and telling it a little bit about how to parse the structure. And each of these follows basically the same form. You'll see that. Just a different file for each of the different tables. So when I run this, those have now been created. If I look down in pipelines, I'll see they're created, but they haven't started. If I minimize that, you'll just see a little bit of the stats that are provided on those objects that were just created there. So next, I'll just start these pipelines. Take me back to Studio. It's pretty simple. Start all pipelines in this schema against this database, TPCH. And I'll run that. And as I look at that, now I see that they're all running. Great. So that's going to take a little bit of time as this data is being ingested. So while that data is being ingested, we can do some interesting queries against the data that's being pulled in. So I'll come back to Studio, and I'll run just this query against line item. But I'm doing computation here, you know, sums, basic metrics on a pricing summary report. 60 to 120 days here. That's a typical kind of query, sort of like the retail use case I mentioned earlier. And again, I can look at this below, and I can see this ran, I got 4 rows as the result, about 3 seconds. If I run this again, it went from 3 seconds to 200 milliseconds. That is the effect of that code gen, which I mentioned before, where the query is compiled. And if I run again, I should see similar performance to that. So in the 100 millisecond range. A little variance there, but not in the second range as I saw. So quite a big difference from that code generation. And we're not, you know, writing this data to a materialized view or anything like that. You know, the queries are being done again, and the aggregation's computed as this query is run. So let's show another one with top 10 unshipped orders. We'll minimize this. And doing something that is a little more interesting, where we're joining data from across 3 tables: customer, orders, line items. And we're doing calculations, and doing a sum here as revenue, and grouping by each of these different columns and ordering. So we're asking the database to do a little heavier compute workload to do this. SQL has the declarative power to do a lot of this processing that, again, in the NoSQL era, we were having to write in applications in an imperative way, not in a declarative. We're writing this in code, fetch this data, then iterate through the rows, do matches, pull this back. You know, we were becoming database designers in our application when we weren't experts in database design. It's not easy to do. SQL provides this declarative power to do this, but now you see that you can do this and expect it of a distributed in-memory and column on this database, columnar database, and not have to do this yourself in your application code. So we'll run this, and we're returning, I think I have a limit on the 10 rows, that's right. And we run it again, we'll see. Let's see what happens there. But we're asking it to do a little, and each time it's computing this, right? So a few seconds, but we're asking it to do a lot more in terms of the scans that have to be done, the aggregation, the range searches, etc.
What is the size of this data?
This data is a good question. The question was, what's the size of this data? It's about 100 gigs is what our sample set is here. These are stored, if you look at the earlier queries I ran, let me scroll up to the creation. Let's just look at line item, for instance. You'll see that it's a column store. So you're getting compression on that. So it's going to be smaller on disk in the column store and partitioned by or sharded by order key in this case. So, yes, what's the question?
So, by this time, the importing finish of all the data?
Good question. So the question is, has the pipeline finished the import? Let's take a look here. And will we see the completion? They're all still running, and I don't have, we have another view called ops that can show us how many rows are being ingested. I'm not showing that in Studio. I could run this from the command line, but probably at this point through just looking at the data set and looking at the node, we can infer it sort of indirectly through how busy the nodes are here. But really the view is through, we have a command line interface that would tell you what that process is, and also another UI called MemSQL Ops that tells you more details of what's happening in the pipeline.
So if it didn't finish loading the data, you're getting partial results on those queries?
If it weren't finished, I would be getting partial results for that. That's right.
And how would you know that's not the real answer?
So the question is, how would I know that it's not the complete answer? Well, it's the answer at that point in time for the data I have, right? So that's part sort of a, it's use case dependent as to if you have written a query that provides the right answer about the business. If the point is that this is really meant to be showing the changing state of these business objects. So order, what's the state of order now? So back to that Fanatics use case about order visibility. What's the last data I have now? Not what I had in a batch process from 6 hours ago, but from the stream of data that provides, or the multiple streams of data from the different systems, since they're a multi-channel business, they'd be coming through all different channels, probably sourcing from different warehouses. From the best I have from the availability of those data feeds, this is the point in time. So that's still, so you have to think about that with those queries, but don't miss the point that the big idea is that you now can get closer to the real world physical position of an object or a shipment or a plane or whatever sort of asset needs to be tracked or metric needs to be tracked with the granularity that you need. Good question. So that's, we have, you can continue to run queries like this and see this, but this basically gives you a good view of what Studio is, how pipelines work in terms of ingestion, and that concludes the demo. Let me go back to the slide here, and I would just, I covered a couple of examples of what we call more generally operational analytics. And you might be asking yourself, well, what is MemSQL good for? I can do transactions really fast. I can do analytics really fast. I have applications where I might want to do those together along with full text query search, geospatial, maybe not in the same application, but among different applications, I'd like to use the same data store with this kind of speed to do those different functions. Really the sweet spot for MemSQL is in that combination of operational analytics. Some people call these real-time applications. If you think about Uber, who uses MemSQL in a way that, they are a two-sided market, right? Basically, they've got to balance the supply of drivers with the supply of riders. And if one of those is out of balance, then one of the two parties is sort of upset and thinks this is terrible. If you're a driver and there aren't enough riders, you're thinking, I'm wasting my time. I'll switch to Lyft, or I'll switch to something else, or just spend my time doing something else. Same on the rider side. If you find that there aren't enough drivers, right? And it affects, what the fare is going to be. So there's a lot of dynamic balance happening across different factors that are continuously changing in a neighborhood by neighborhood basis, and a citywide basis, and then for them all over the world. So the whole business model rests upon this balance in resource availability, if you think about it more generally. And this is like one of the only ways that you can manage that kind of business model. And more businesses who have continued in that journey from the early days of consumer-facing eBay, Facebook, Amazon, etc., and brought their business right in the hands of all of us via mobile applications, that's the kind of interaction that's expected. And so you've got to, it's more and more about the heart of the business, the way to ensure that you're giving a competitive product and service is to be an expert practitioner of operational analytics. And that's our sweet spot, because you have the combination of big, fast data that has transactional needs. It needs immediate consistency. It can't have dirty reads. The data must be correct, must be consistent. You cannot lose data. It's got to be durable. It has all of the ACID, principles supported, but allows you to also do transactions without having to have as much data movement to other types of data stores. If you don't have that, and we like to think of that in sort of the shorthand way we think about that is analytics with an SLA. I've got to know now, because I'm going to have a human decision to make, or the system will change some balance between other resources. If you were to say, well, I like the speed of that, but I don't need it now. It's no benefit to the business if I get it now, or an hour later, or tonight. Then I would say a traditional data warehouse might be good enough, or other solutions. But where you have this need, this business driver for in the moment state of the business, state of the asset, state of the truck, the plane. It could be a fraud detection, cybersecurity, the state of an account and the behavior in that account. Oh, there was a credit card that was swiped in Singapore, and 6 minutes later, the same credit card with the same CVV was swiped on Canal Street. That's anomalous, right? But if you detect that the next day, it's sort of the fraud's happened. So the moment MemSQL allows you to reduce the time to detection of the business scenario, any kind of context that you might need. It doesn't restrict you to the number of data sources you might need to bring in to make the best decision. Like oftentimes, because of previous solutions approaches, you had to sort of restrict and then make a judgment call. You can bring all the data and reason on it, but keep it simple for the application. So we recently published this ebook. You'll find it on our site. It's an excellent sort of overview of this area of operational analytics. And what I just showed you with Helios, you can try that for yourself. There's an 8-hour free trial. You can spin it up. You can run through those. You can insert your own data, pull in your own data from Kafka, S3, etc. Or download the 7.0 beta, install that in your own VPC, your big hardware. Or do this in Docker. You'll find this cluster in a box that we provide for Docker. So thanks for your time. Thanks for your attention. And I'm happy to take questions at this point.
Thank you, Dom. Domenic, Ravita. We are going to now give away, well actually, you know what, before I say what we're going to do, Domenic will be here for one-on-one questions, so don't leave without coming to talk to him. But we are now going to give away the raffle prizes. Who's got the glass bowl? There's nothing in there. Oh, there is something. It's a reflection. Okay, let me grab the prizes. Hold on 1 second. Let's see. For a Fanatics prize, actually, can I ask you just reach in and mix it all up? Can I ask you to look that way and pull out a card? Is there for a Fanatics gift card? Just one? All right. And just read that aloud, please.
Patel, I can't read the last name.
Patel, I can't either. Delarme? Is there a Patel? What? I don't know. Is your first name Patel? All right, he's going back in. All right, look that way, reach in, grab out a card. Who's that?
Patel.
Oh. Just put that one aside. Reach in, grab another one. Well, I threw it back on the top of the pile.
Elliot Norma.
All right, Elliot, come on up. All right, let's see. Fanatics one. That one's yours. Thank you. All right, and can I ask you to look the other way, reach in, grab out a card. Read it out. Wait, before you read it out, this is for the Uber certificate.
Ashwini Walmart.
Ashwini. All right. Grab out another one. People losing out their prize.
Andrew Choi.
Andrew Choi. All right. That one's yours. Congratulations. And look that way. Jim, grab a card.
It's my own card.
Nice job. All right. Congratulations. No, that's fine. You were looking.
You win twice.
Okay, guys. So our speakers here for one-on-one questions. Feel free to come on up and ask. Thank you all for coming.